Sorry, everyone. Look, we're a little behind. Go ahead and get things started. Come on, folks. Camera's rolling, so it's go time. All right, so I've got a good, I can fill up pretty much the hour with example questions. These reactivity, delta G things, several examples. Then you do have a Kirchhoff's law. That was kind of a last week thing, but it's one of the, it's a harder one where you have to figure out where delta G is 0 by changing temperature. So that's kind of a pain in the ass. So I was going to do several of these types of questions. And then the Kirchhoff's law, make sure you know exactly what to do. But as I stated in the email and just earlier, hasn't been a lot of questions from you guys, so I was hoping maybe you want me to, I'm just throwing something out there, to work a problem from the second test, anything, go over something, nothing, really, we're okay? Okay, well, I'm glad you're okay, I hope you feel it, I hope you are okay. You know, that's important, but if not, yeah, I've definitely got enough material. Actually, the days of yore, before I had built up so many notes, I often really wasn't saying much at these times. I just didn't have material prepared to talk about because it's just so much stuff. Okay, getting back to this guy here for water. So that was water decomposing. And I should be doing this. And I am going to work that problem, the natural log problem, in a minute. But what I wanted to go back to was talking about the representing decay as a mole fraction component and the pressure, to figure out what pressure does. I kind of just got my tongue twisted there towards the very end. So what you have to do with these types of things is you really need a computer to start solving them. And you're going to need that for P-Chem Lab. So what you can do is graph this sucker versus alpha. And alpha, again, always goes from 0 to 1. And what you find is that it does this. It actually will go to infinity at 1. So the point here being, if pressure goes up, kappa goes down, and that means that alpha goes down, right? To make this go down, you have to go this way. So that means that the extent of reaction is less. So higher pressure favors the reactant, right? This represents how much goes away. It's gone down with increasing pressure, and therefore I have more of this. Because if I had more of this, I'd have higher pressure on top of higher pressure, which Le Chatelier's principle fights against. Okay, so anyway, this makes sense. So, because I might bloody likely say, how does the equilibrium of this, and I'll do a gas phase reaction, change with pressure? Anyway, all right, so prepared questions. Let me start with a couple of different ones. These are from last year's homework. That's why I was late. You know, I always write different homeworks when I can. You know, sometimes I like, what's entropy is a question. You know, that's not something I can like change every year. But this was last year's, well, 2 years ago. This was the question they had on the homework. It just took me a while to find another question to ask you. So we're going to analyze this one. And this is an important atmospheric reaction. It has a lot to do with the ozone layer. NOx's, so any nitrogen oxygen, and because of nitrogen's ability to form very highly valent compounds, you can form several different nitrogen oxides. That's the brown stuff that spews out of your car tailpipe. If you ever land in Houston, when you're going down, at one point you'll see nothing but a brown sky. That's because of all the pollution. And those are NOx's, largely doing that. And they smell very bad, and they're incredibly bad for you. You start throwing chlorine into the mix, and you got some really nasty stuff. Okay, so we're going to start with N moles of both reactants. We're going to be at 1 bar and stay at 1 bar. And I'll tell you what to do when you don't stay at 1 bar because you're working in a metal box. This will be in the atmosphere, and we're at 25 degrees. So we can use the numbers in the table at the back of the book. So here's how I do all these. This is on the test, by the way. There's no doubt, not this thing on the test, but something is on the test. You make a table. Sorry, equilibrium. And then you're going to talk about mole fractions. And and then we're going to do partial pressures. Okay, now I said we'd start with n of this and n of this. And again, I make a table for each species. NO2, and Cl, and O. Okay, make a giant table. I don't think I made the table big enough, actually. Say, these are big tables. I'll do this one first. And this will help you see the, what am I saying, the blah, 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 the answer keys. This is how the answer keys will work. Okay, now I'm going to start. Now, part of this is figuring out a model that's sensible. Now, you almost always begin the same way. I'm not going to say n of this and n half it, n of that. No, this is already hard enough. So I'm going to start with n of that, and I know that if it all reacts away, I should end up with 0. If it doesn't react at all, I'll have n, and that does this. And again, alpha goes from 0 to 1. So that makes alpha the percent of the reaction that's occurred, right? If alpha 0, you got nothing. If alpha 100%, 100% reactivity. So it's very easy to interpret, but you've got to make certain that you can express everything in terms of alpha. Now, again, it's sensible. It's just obvious. But it can get complicated, especially if you have this, squared and all that. So you just got to look out for that and just think about it. Okay? And I'm going to get n alpha of this and n alpha of that. Okay, there we go. Okay, mole fractions. The next thing you do is you total them. Okay, 2n, 1 minus alpha. I just added the first two terms. Add the next two terms, 2n alpha. So this is 2n minus 2n alpha plus 2n alpha, 2n. All right, so that ends up being very easy. Okay, mole fractions are this over the total. And that's going to be 1 minus alpha over 2. I've just canceled out the n's. So it never, if you do it right, the n's never stick around. And this is going to be the same. This is a relatively easier one. And then this is going to be alpha over 2 and alpha over 2. Okay. And then the partial pressures are the same. Usually I keep the n's here. This is why I have the second line. You don't really need it. So I don't know why I'm doing this right now. It's kind of stupid. Alpha over 2 times p. Now, if you, when we define k, here, I'll leave this up here. When we define k, you need to have the partial pressure divided by the initial partial pressure, which is always 1 bar. Because all the numbers have been fixed to make certain that that is the correct number to use. Okay, again, I'm going to use my little odd symbology for this. Ai, the stoichiometry of I, which is all 1s in this case, is I'm going to throw examples where you don't. I know that one looks weird. That's what it is. Okay, now this ends up being, okay, so I've got alpha over 2, p over p naught. And the same for the other guy. Now this is products on top. There's 2 of them, and they are identical because it's a 1-to-1 match. And the other guy's on the bottom. 1 minus alpha over 2, p over p naught. 1 minus alpha over 2, p over p naught. And again, that's so units cancel, and who cares? Okay. So now, the thing is, keep these guys on top and flip these to ones on bottom. So alpha, why don't I just go ahead and do alpha squared over 4, p squared over p naught squared. And then it's always a bit of a pain, p naught over p. I'm doing this one, but I'm flipping it. 2 over 1 minus alpha. All right, yeah, 2 over 1 minus alpha. P naught over p, 2 over 1 minus alpha. Okay, canceled, 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 canceled. All right, this is a friendly one. The pressure's canceled. It gets much, it's not really much harder when they don't. I'll show you how to deal with that. This is an easy, relatively, I know it's a lot of stuff, but relatively this is an easy example. Okay, I've got, 2, 2, 4. That leaves me alpha squared over, okay, so that was canceled. Oh, yeah, God, I hate these. I know I did them in middle school, but I still hate them. Let's see, we got 1 minus 2 alpha plus alpha squared. Okay, there we go, and that's K. Okay, now I don't think I set up the question very well. The question is, what's the extent of reaction at 25, 1 bar? Actually, we could have gone off 1 bar because all the pressure is canceled, but they don't always, so you can't just assume that. Okay, so now given, I'm writing the question I should have at the very beginning. Ln K is minus delta G over RT. What I'm asking for is, what is this? And again, we're at 1 bar, doesn't matter in this case, 25 degrees C. Because we're at 1 bar and 25 degrees C, what I've done in the previous question is I've asked you to do a Hess's law of delta G. In the previous question, I asked you to do a Hess's law of delta G. You calculate what you calculate, then you do the next question, and then it's given to you. And in this case, it is, sorry, this should have been up there at the beginning, minus 23. 23, and that's always going to be in kilojoules per mole. Okay, again, the previous question asked you to solve that, and you know the next question, it has it. And there it is. Now, give me alpha. Now that you know that, R is R, T is given. This is defined. I got a 1 equation with 1 unknown. And let me do this the way that we did it back in the old days of 1990. I was actually one of the first people to use the internet, by the way. I was at 18, and the internet had just been invented because the military had released ARPANET. ARPANET was the military's internet. They opened it up to the public, that's the internet. I think I used it within a month of its release to send an email to a stranger. Very lewd thoughts. Anyway. Okay, sorry, I just got to find my notes. Okay, so what I'm left with is, therefore, natural log of alpha squared of 1 minus 2 alpha plus alpha squared is equal to minus delta G over RT. Okay, minus. Okay, got to be careful. This is the number one thing that you'll start to get wrong. Minus, positive. 23 joules, and that's kilojoules per mole. Everything is, I got it right. That's true. Everything is going to be per mole. Then I got 8.314 joules per k mole times 298.15 K. All right, if I've done that right?
Can you write the joules to kilojoules?
First mistake you're going to make, because I made when I was designing these questions before class, I was screwing it up. SI, stick with SI. Remember, the data tables are a big trap in all of these questions. The data tables are in kilojoules per mole for enthalpy and Gibbs energy. They are in joules per mole, joules per k mole for entropy. These questions, that's a trap, so look out for it. Minus, minus, that's another trap. It gets a lot of people, including myself. Okay, so what you end up with is, this ends up being 9.28. I am obsessed with units, but there are no units, they've been canceled. They need to, because it's equal to the natural log of something. This has no units, neither can this. Now what I'm going to do is raise everything to the e power. Maybe be this. Now be careful, alphas, my alphas look like 2s. All right, so now I've got, but what do I want to do here? I want to go ahead and do 2 steps of algebra at once. So that's, I'll toss this up in a second, I'm done here. Is equal to 1.07 to the 4th power, times 10 to the 4th power. Okay, that's that. And times 1 minus 2 alpha. Okay, I'll continue on the next board. And I've learned not to work downward. That was kind of stupid because when I looked at the movies, I realized that that was actually kind of hard to follow, actually. Just left, right, up, down. And okay, so where did I simplify this? Okay, so what you end up with is, again, do some algebra. 1 minus 1.07 times 1/10 to the 4th alpha squared plus 2 times 1.07 times 10 to the 4th alpha minus 1.07 times 10 to the 4th equal to 0. Now what do I do?
Quadratic.
Bane of every 4th grader. Minus b minus square root of b squared minus 4ac over 2a. Sorry, plus minus. Okay, now, if you're going to do it this way, that's great. I wouldn't recommend it. That's why the internet exists. That's why they put Mathematica online. Mathematica can solve this for you. But you got 2 answers. So now, I actually did the quadratic equation. And so A, B, C, and make sure you keep it straight which one's negative and which one's not. What you're going to get are 2 answers. Because there's 2 possibilities. Which one's correct?
Second.
Why is that?
First zero between 0 and
Right. Has to be less than 1. So this reaction proceeds to 99%. And it kind of makes sense because that's a decent level downhill. And that's not bad. That's not bad. I would expect this reaction to largely go to completion. I'll even do another one where it's even more significant. So, better yet, on the homework, I have a link to Mathematica. And Mathematica has several different flavors, so I sent you to the solver. And so on the Wolfram site, all right, it's going to have this little prompt at the top, so you just click on my link on the PDF. It should take you there, even in the PDF. I don't like that Adobe too much, but it does a couple of things nice. And the way you put it, in the little box, there's a little box, you're going to write solve, space, and this is a bit tricky. It's a bit tricky, and it's temperamental, by the way. It's because when they gave it away for free, they gave it a stripped down flavor. So it's not so good at interpreting what you're telling it to do sometimes. Okay, this is the language that it understands. And you should be used to this at this point. It's kind of sensible. All right, you hit enter, and then the return is X. It's going to be kind of complicated. 043. And then there's another solution. It knows that there's 2 solutions. Gives you the 2, you pick this one. Okay, so on your homework, what I'm expecting you to do is to get me to there, get me to that part, and then say, well, then I use mathematical. And then to write down the answer, whether I'll see whether you got it from a friend, your friend's Mathematica. So it's the same thing. I'm fine with you at that point, if you choose to use Mathematica. I do want you to know that you can do it, all right? Back in the day, we had to do this, and it's sucky, but it's not that bad. So I just want you to know there are simple solutions that you can use your calculator, but as I've told you many times, I do believe that we build tools to be used, so use them, but you have to use them right. So it changes, that's why it changes the nature of the question sometimes. Because like I say, why did we build all this if we didn't use it? And a lot of constantly the older guys, they think that everything still needs to be done with the slide rule. But that's how shovels get blown up. So anyway, okay, let's work a harder one. And this is the one I just did, but I'm going to go a little further with it.
If you left k equal alpha squared over 1 minus alpha squared to be a brought the 2 to the front.
What?
Okay, if you left k
What,
as equal to,
where?
and ln, see where this, so if you left it as alpha squared over 1 minus alpha squared, and parentheses squared, can you have just brought the 2 to the front? No, you can't do it.
No.
So I know how,
You can.
if that was 1 minus alpha, in parentheses squared,
Oh, yeah, it's the same thing. Yeah, this is 1 minus alpha squared.
so could you have brought the 2 to the front, and then left it as alpha over 1 minus alpha?
Not the 2 to the front, maybe.
Yeah.
Oh, no, it'd be 1/2, it'd be 1/2. This is a denominator, right? No, actually, no, you
They're
couldn't,
both
no,
squared.
you can't do that, no. The whole, you're doing this. Right?
Yeah.
That B encompasses all of A.
Okay, both squared.
They're both squared? Wait, you're right.
There you go.
That's true. You could have done this, and you could have done this. Yeah, that does work. And then, you don't have a quadratic equation, do you? It's still a Bismarcker. Yeah, that's clever. Yeah. I still recommend just getting Mathematica to solve it. Because the good thing about Mathematica is, no matter how good you are at simplifying things, Mathematica doesn't care, you know? So, yeah, those are the kinds of tricks like when I was your age that we had to do, because there was nothing like Mathematica at the time. Well, they were just being invented. So, yeah, I'll actually work that one when I go back and actually see if there's, that certainly looked right, I'm sure it's right. I'll actually work it when I go back to my office and look 100%. There's always multiple ways to do this. You guys are actually really good about coming up, like on that last question on the test, prove that adiabatic divorcible is 0. There were 5 different ways to do it, by the way. You found all of them, which made grading it really hard. Just wanted you to know that. Now, on your homework, you have this, but it's not the same. You're going to work this problem, but I threw a little, I like to work similar questions during these sessions, but I'm not going to work the exact same question. So if you look at your homework, you got 2, 2, 1. I basically gave you twice the reaction. It does change it changes the result if I do that. It seems like it shouldn't, but it does. So this one is slightly harder to work than the homework. Now I know I just did this, but I want to do the table. I didn't do the table. And the table makes everything very easy. And so the initial, at equilibrium, this is the equilibrium. Now again, I'm going to start with n, and I'm going to lose that much. I'm gaining this much. I'm gaining this much. The total. Total again is n minus alpha n plus alpha n plus 1/2 alpha n. The total is then plus 1/2 alpha. Is that right? Yeah. And plus 1/2 alpha. Yeah, okay. And that makes the mole fractions 1 minus alpha over 1 plus 1/2 alpha. Okay. And then this guy's going to be alpha over 1 plus 1/2 alpha. And this one is a little bit different. So 1/2 alpha okay, let's do the partial pressures. All you do is you just write these down. Now, don't forget, these guys, this one's going to be different because it's going to pick the square root. And you see why when I do the opposite, when I have 2, 2, 1, nothing is square rooted. Some things are squared, but square roots are hard to deal with and squares are not. So that's why your homework is actually slightly easier when you're going to do the same thing. And without belaboring the point, what you end up with, because I just did it right, so I'm just going to go ahead and give the answer. I'm going to give the answer, wait, did I? Sorry, let me double check something. Did I? Yeah, I gave the right answer. Yeah, I gave the right answer. Okay. So K is it's alpha to the, did I write this down just in the last hour? Because I'm kind of blanking out. This is what I wrote, right? Alpha to the 3/2. Or wait, did I? I'm sorry, I don't know why, I'm just blanking out on this. I did or didn't?
Yes.
I did? Okay, sorry. Yeah, I mean, you saw what to do. It's painful, but there's a lot of algebra. Sorry, wow, I don't really remember it better than that. So, we got alpha to the 3/2 over 2 plus alpha to the 1/2, 1 minus alpha. And that's going to be, I'm going to have pressures. But the pressures, again, did I say, we're doing this reaction, we're going to be at 1 bar at 25 degrees. So the pressures will all be wiped out. And let me actually see what would happen if I did not do that. I would actually have, okay, I thought that was right. Okay, so again, on the homework, sometimes I'm friendly, and I'll say that I've set this up, and the pressure will be maintained at 1 bar by this complicated machine, and that means that the pressures go away. And I'm going to work a problem where they don't. All right, so therefore I have natural log, okay, and delta G is, God, sorry, my notes are being painful today. I wrote these before class, so I'm not actually familiar with them, so I'm sorry about that. Yeah, 237 1 kilojoules. So L and K is minus 237,100 over 8.314 times 298.15. Okay. Minus is plus. And this ends up being, we're at 95.65. Okay, then we take E to each. So I'll look at E, and therefore you're left with alpha to the 3/2, what I just wrote, 2 plus alpha, 1/2, 1 minus alpha, is equal to, and you're going to love this, 3.471 times 10 to the 41. Okay. Now, what did I do here? Mathematica. I don't think we have a quadratic equation, although not quadratic equation, for alpha to the 3/2, let alone this other stuff. Yeah, I guess algebraically it can be solved, but I would rather not, so I didn't. So I plugged this into Wolfram. Oh, and how did I do it? Solve, so you write solve, and then, so for Wolfram, you write solve, and then I did this. Wolfram can be very temperamental. Sorry, let me try to stick this, because you've got to get this just right. And then, I'm sorry, I'm having to go down here. So this is all one line, sorry about that. Equal, sorry, I made a mistake. 2 plus x. Made a mistake, 2 plus x. It likes x. All right, e to the. Okay, so that's what you type into Wolfram. Again, you got to be careful about this. When these get really long, Mathematica starts to really care about where the parentheses are. And it'll also rewrite the equation for you, its interpretation. It often does it incorrectly, but it does understand it correctly. It doesn't represent the equations correctly, sometimes. So again, if you're having trouble with it, because they gave it away free, it's very temperamental, and it's very sensitive to how you type things in. And I also noticed is that it hangs a lot. It just says it's calculating forever. Sometimes it's just looking for a solution and it never finds one. Sometimes it's just the little applet is screwed up, and you just close the window, start over, and then it works. Okay, so solve, hit the button, and it says x equals 1. Okay, what it's really doing, and therefore the extent of the reaction is 100%. What it's really doing is that the answer is really 0.99999999999999999. No, wait for it, 99. So it's just it's huge. It's basically 1. Mathematica eventually decides to stop calculating and say, well, 1,000.9s is just the number 1. So that's why it spits this out. And this again is expected because that delta G, that's gigantic. Absolutely gigantic. So I am not surprised that this reaction goes to 100%. Wait a minute. Am I on that right? You saw nothing. Sorry, folks, I gave that. I should have given it a positive. That's in reverse, my bad. Okay. Sorry about that. It does matter whether we've got products or reactants, but then hold on, I did the freaking things wrong. No. You know what I did wrong? You know what I did wrong? All right, so I've set this up correctly. Sorry about that. You know what I did wrong? I used the wrong delta G. I should have used positive. That's what I did wrong. Sorry about that. Tell you what, I'll fix my notes and send them to you. Sweet. I just wrote these, that's why I'm screwing up. It usually takes me a couple of years to get these right. Try being in my shoes, all right? So the handouts that you have, by the way, I don't think there's any mistakes with them, like in the handout section, and hopefully not the turkeys and chickens either. Those literally are like 6, 7 years old. They had plenty of errors when they were first written. This is 5 hours old, so it's got plenty of errors. Okay, so yeah, the reason I realized that something wasn't right was that a negative 237 is absolutely enormous, but I know that hydrogen and oxygen are going to form water. I know that that's thermodynamically downhill because I happened to remember like weird things, and I remember the delta G of water, because the delta G's of this guy are what? In the table? They're 0, right. I happen to remember it's minus 273, but that's the formation. That's this guy over there. Okay, so anyway, so if I had done this correctly, for water forming, where am I at? All right, for water forming, the extent what I was actually solved for was this, and that's just that minus sign screwed me. I just want to point out something because you're going to do this in 344. This says 100% water forms to an extreme extent. So if I mix a gas, hydrogen and oxygen, does it form water perfectly?
No.
What does it need? It needs a spark, right? You got a balloon with hydrogen and oxygen? It doesn't form water, but I just said, all right, just forget the screw-ups, all right? Had I done this correctly, the thermodynamics say that it's going to form 100% water. Yet I have a balloon that's full of hydrogen and oxygen and nothing's happening. What am I missing? Well, I just said it a minute ago. A spark. And what happens? Kaboom! Right, because it so violently wants to form products. When you have thermo that's that strongly this way, that's kind of an explosion. Plus, your products is a gas as well. So now the point of this is that when you take 344, that's the kinetics section. So the funny thing about thermo, this is really important. Thermo says that balloon will eventually form water, but it never said how long. It may take 1,000 million years, but it will do it. But it never says, thermo never tells you how long it takes. That's kinetics, and that's 344 for you. Anyway, now let me point out just a couple of other things. Seeing how I'm really screwing up my delta G's, let's do a reaction. A goes to B plus 1/2 C. So what I've done is I've made up a equilibrium. I've made up a reaction which is identical to water, what I just did. And I've made it up because let's say that it just turns out that delta G was 0. God knows I'm good at making up delta G's. Delta G was 0. What do you get? In this case, the expression is identical to what we just did. Except it's going to be equal to e to the 0, which is 1. Again, I put that in Wolfram, solve for it. And it says alpha is equal to 2/3. It actually says 0.666666. It's doing it numerically, so it doesn't understand fractions. So that's kind of neat. So I said, if this thing's at equilibrium, what is my extended reaction? It says 2/3. So if I get 2/3 of this and then 1/3 of that, I got 1 mole. I just thought that was kind of neat. If I start with a mole here, I end up with a mole there if I'm at equilibrium. This is the kind of neat things you can learn with this. The other example, is, although I screwed it up, was kind of extreme. And that's because the thermo is very strong, positive or negative, especially if it helps if you get it right. And I thought it was more instructive to see what happens in this hypothetical. I was kind of looking for a reaction. I wanted to show you something real, but I just couldn't find a reaction that is basically delta G neutral that occurs in the gas phase. I was just Google searching. Then I didn't find it. Okay, now the last question I have is, I'm running out of time. I'm just going to have to send you these notes. Well, I got 2 more. I'm going to show you one and then show you another real quick. And that is, where am I at? Okay, let's, I'm sorry I'm running out of time, you know I don't like writing over my own derivations. All right, before I decided that the pressure was going to be 1 bar, I was in this situation. Now let's say that the reaction's in the metal box. Okay, sorry. This is again for my hypothetical. Okay, it's in a metal box. And as I form products, the pressure is going to change. It's going to go up or down, up. It's going to go from 1 bar. I'm going to start with 1 bar here just because. And I'm going to end up with, if it goes to completion, 3 halves, right, 1.5. Okay, so that means that this thing is changing. And this guy, again, you can always forget about it, it's just there to make the units work. Now, if this thing is actually going to change, it has to be 1 if alpha is 0. It has to be 3 halves if alpha is 1. Now, on your homework, you're going to have to do a similar problem. It's not the same, but what you got to do is you've got to let this thing scale from 1 to 1.5. Not that it's necessarily going to go to completion. And now you've got to put in a function of alpha that does this. And these are bars. Where I'll be at later. Anyway, all right, so can someone give me a function to put in here that goes from 1 to 1.5 as a function of alpha? Okay, if alpha is 0, then the pressure is 1. So give me something to at least put down right now. What? Hold on, let me just get you started. 1. Right, if alpha is 0, then the pressure is 1 bar. Now, alpha is 0, so I can't multiply it by alpha or some other function of alpha. All right, see again, because alpha is 0, I've got to have the number 1. That means I have got 1 plus something. Now, if alpha is 1, this is 1 plus 1/2. So what do I add? 1/2 alpha, right. Okay. Now your solver is this. Sorry, let me remind you, e to the 0. Solve. Alpha is, where am I at? 0.638. Okay. So, as opposed to water, if I had not done this, the answer was 0.6666. So, see what happens here. If this reaction occurs and the pressure is maintained, I'll get 0.66666 of this, 2/3 of this. If I put it in a metal box and I let the products pressurize the container, I get less of them, right? Does that make sense? Right? You gotta explain that, right? Because the pressure is the same thing as increasing the pressure. Well, pressure is a product. You add product, you're gonna actually swing back towards reactants. That is smaller than that, and this is the extent of the reaction. The reaction did not go as far because the pressure drove it the wrong way. And so it all makes sense. Well, with that, folks, yeah, we're pretty much out of time. I'm going to fix this and send it to you. So, because there's one other type of question that's kind of hard and I just didn't get to it. And I also have a Hess's Law example. You'll have that in half an hour or so.
Is it like how do you test
No.
Okay, what's up here?
Oh, I thought it was 8 tests.
The best way to do that, I mean,
I'm like, you're like,
the best way to think of it is alpha is 0, reaction.
what's the better? I don't like that.
Oh, that's right.
Javier.